Assalamualaikum and hi everyone. In this video, I'm going to cover topic 1 and 2, which I already combined into one topic only. So the name of the topic is functions of several variables. So at the end of this topic, you should be able to understand the function of several variables, able to do partial derivative and successive differentiation, and you should be able to estimate error using exact differential. Okay, so let's go to the first subtopic, function of two variables. So in many real-world applications, functions are expressed as more than one independent variables. For example, in a furnace, temperature, which is the dependent variable, depends on two independent variables, which are position or location and time t. So this is the photo of a coal-fired furnace, where combustion of coal happens. So when we want to find the temperature inside the furnace, of course it will varies depending on the location of the not the location of the furnace, depending on the position inside the furnace. So if we take a reading at the top part of the temperature, it will be at the lower temperature compared to the center part of the furnace. So this is the view of combustion inside the furnace. So usually the combustion occurs only at a certain point. So that is where the temperature is the highest and the surrounding temperature will be a bit lower compared to the center. So when we so this is the function that describes how the temperature change depending on the position and time. This is actually a simplified version. In real life, the temperature not only depend on position and time, but it also depending on the moisture content of the coal. Maybe the type of coal also affects, maybe the ignition temperature. So there are many variables that can affect the temperature. So that is why function of multiple variables exist, because of course one variable, the dependent variable, which is currently we are talking about temperature, depends on many factors. And if we are looking at only two variables, which are position and time, we will get this equation of function of two variables. So this is the temperature distribution in a furnace. If we try to draw the distribution of the temperature, we can see that the inner part here is the hottest. You can see here at the scale here, the highest temperature is red color, around 1700. The lowest is blue color, 240. So the highest temperature is at the center, and if you go further, the temperature becomes lower. And this is the temperature distribution at different location. And if you take it at different time, you actually have different temperature profile for each second or each minute that you take. So this is how you model the temperature changes in a furnace. Okay. Now, how to represent or how to see the function of two variables graphically. So as you all already know, function of one variable is represented using a 2D curve. So this is a sample of a function 3x minus x cubed. So this is S shape here. And this is a sample of a function of y, which is negative y squared. So for one variable, it is quite straightforward, just a flat 2D curve. But when it comes to function of two variables, you will have a 3D curve, 3D surface plot. Or you can also represent it using contour plot. So these two are coming from the exact same function, which is this function, 3x minus x cubed minus y squared, which is basically this function is a combination of this one, 3x minus x squared here, and minus y squared. So when you combine these two functions, you will get this this function that looks like this when you plot it in 3D surface plot. So in 3D surface plot, you will have three axes instead of two. We'll have x, y, and z. Okay, so you can use either one, but I prefer to use surface plot because it is easier to understand. Now there is several online graphing tool for you to visualize 3D graph. I usually use Desmos. So let's see. So this is the link will lead you to this web page whereby you can type your function here. So I already typed my function. So this is what it should looks like. And you can adjust the ABC values so that you can visualize the overall shape of the 3D curve. So this depends on you. How do you like to see it? So changing the ABC helps you to move around, okay? So you can zoom in and zoom out to see how is the 3D curve shape, how it looks like. So this is the shape of this function, whereby this function is a function of two variables, x and y. But what if you have more than two variables? So if you have three, for example, then you will have a 4D graph, which is very complex and will I would just want to show you, but we will not, it is not covered for this course. But this is how a 4D graph looks like. Okay. Let's go to the slide. Right. Now, when we have a function of more than one variable, we can have partial derivative, whereby we do differentiation only for one of the variables. So we have a function of two variables, but differentiation we do only for one variable. So, for example, if you have a function of z equal to fxy, so if we do differentiation only with respect to x, we will have a partial derivative del f over del x. This is the notation that is used for partial derivative with respect to x. And del f over del x can also be expressed in a simpler notation, which is f subscript x. So x means that we already do first partial differentiation to the function. When we do partial differentiation of this function with respect to only y, then we have del f over del y, and also this notation can be used, which is f subscript y. Okay, this is the limit equation that is already explained during Maths 1. So this is basically just saying that it uses a similar concept to differentiation, but when you do differentiation with respect to x, this y will become constant. Okay, let's go to example 1. For example, this function 3x squared plus 2xy plus y cubed, and you have to find what is the del f over del x and del f over del y. So if you want to find del f over del x, you have to do each terms individually. So for the first term is quite straightforward because only x term is involved. So you just have to find differentiate as usual. But for the second term here, you have 2xy. So y, we have to consider it as a constant, and when it is constant, we can take it out from the derivative. So 2y here in front, and you only do differentiation for x. The third one is y cube. So y cube here, this is quite tricky, okay? Y cube is also a constant, so you have to take it out. When you take it out, and this will be del of 1. If you differentiate 1 with respect to x, you will get 0. So when you multiply 0 with the y cube that you already taken out, that you should get 0, not y3. Okay, so the answer will be 6x coming from the first term and 2y from the second term. The third term will be 0. Similarly, if you do for del f over del y, your x now will become a constant, and you take it out from the differentiation. Okay. Let's go to second example. Okay, briefly, when you see a composite function like this is a function of uv. So for doing partial derivative, you can use common rules of differentiation such as product rule, composite rule, and you can use it as needed to solve more complex function. So this is I think this function can be solved using product rule, because this is u and this is v. So this is basically uv prime plus vu prime. U is exponential negative xy. This is u. This is v prime. V prime is only a partial differentiation with respect to x. And this is v, and this is u prime, whereby u prime is only differentiated with respect to x. Okay. And similarly for this one, you have to use product rule. Okay. Now, successive differentiation. Successive differentiation is similar to higher order derivative. For normal derivative, we call it higher order, but for partial derivative, we call it successive differentiation. So when we do for a partial derivative, of this function, for example, we can get 2, right? And these 2 can be differentiated with respect to x and with respect to y. So you will have 2 different second order derivative from here. So you should get del square f over del x square and del square f over del y del x. Okay, and this can also be expressed in terms of another notation, which is fxx and fxy. So please note that for this notation, the positioning is x here is the first partial derivative, and y here is the second partial derivative. Similarly, for del f over del y, you can also do for second derivative with respect to x and y. So overall, if you have one function of 2 variables, you can have 4 different second order partial differential. Okay. Now, let's go to the last subtopic, which is total differential and small error. So total differential estimates the small change in the function's value caused by the small changes in its input variables. Okay. I know this is hard to understand, but it will be a bit clearer when you go to the example in the next slide. So consider a function of u fxy. So the total differential formula is du equal to del f over del x dx plus del f dy del y dy. So this is a formula that is already derived for you. So this is the formula of total differential. This is one of the application of partial differential, whereby you will get a total differential. And from this total differential, you can use it to estimate the uncertainty or error in a function. So small error is a practical application of total differential to estimate the uncertainty in a calculated result due to errors in input measurement. So in any function, u is also always the output, and the independent variable here is always the input. So if we have the error of the input variables here, error of x, error of y, using this formula, we can find what is the error that of output variable u. Let's see an example. Okay, volume of a cylinder, V equal to pi r square h. So assuming that we want to find the volume using manual measurement using ruler, so of course manual measurement will cause small error because of human error. So for example, if you want to find the radius here, radius the range here that you get is 3 plus minus 0.01. 0.01 here is our dr, which is our error for input variable r, and then our h is 5 plus minus 0.05. H is our measurement, and plus this one is our error. So if we have these two information, we can estimate the greatest possible area of volume that we can get if we know both of these errors, R and H errors. Okay. So you just use the total differential equation in the previous slide. So from this equation, you have to find what is del V over del R and del V over del H. You have to do partial differential. Have to find partial differential for this function of volume, and then you have to input this into the total differential equation. So 2 pi r h here is already the partial derivative with respect to r, and pi r square here is the partial derivative with respect to h. And dr and dh here comes from the value of the error here, 0.01 and 0.05. So you multiply everything together, you will get dv, which is equivalent to delta v. Delta v means the error of the volume, and the answer is plus minus 0.345 pi. So this is the answer. This is the maximum error of volume that we can get if we do manual measurement of the dimension of radius and height. But please note that this is not the volume itself, this is just the error. So if you want to know what is the maximum value that you can get, you still have to use the volume of the scene, the formula. Just input the upper value of the radius. The upper value now is 3.3 plus 0.01, that is 3.01, the r here, and the h here is 5 plus 0.05, which is the h here will be 5.005, and then that volume will be the highest volume of cylinder that you can get. This is just the error, not the volume. All right. Okay, that is all for topic 1 and 2. Thank you very much.